on really everything: investigations, design, evaluations, construction, mine rock dumps. He had the opportunity to work with some of, I would say with all of the senior people in the business, Dr. Hook, Dr. Morgenstern, Dr. Peck, Chuck Bronner, John Gadsby, Andy Robertson, Stephen Vick, Dr. Milligan, Marulanda, Stacy, Anisimov, Bean, Jeffries, Byrne. You know, it's just fantastic. I mean, this is one of the wonderful things that one experiences. And Terry has especially worked on a large number of tailings facilities in Chile. And it's a great pleasure to have him here, and he will tell us about his experiences. I wouldn't say in life, but in tailings.
Good morning. So this talk is a result of a weekend activity. It's called Binge Reading Forensic Investigations of Tailings Failures. And it's a subject that there's such a large sequence of forensic investigations that you can spend the whole weekend, get up at 6 a.m. in the morning, pot of coffee, turn the blues on, and you can read for 36 hours and go into the office tired on Monday morning. So lessons yet to be learned is the topic. And how will the past not be our future? You know, it's stark. Everybody hates us. They no longer trust us. We no longer have control of our industry. And so the takeaway message, you can stop listening to this after this, is read. There's all these tremendous reports that we have available that you can learn from. They explain how these failures occurred, why these failures occurred, which are different answers. And personally, I believe that in order to be competent, to be able to practice in the field, we should have read these reports, we should have understood the reports, and we should be able to design our facilities to prevent the failures that are occurring. We've got a draft standard on Friday, so I'm going to talk about requirement 13.4. Implement and identify and implement lessons from internal incident investigations and relevant external accident reports, paying particular attention to human and organizational factors. So this report, or this talk, goes directly to that requirement in the global standard. This isn't something new that we're talking about. You know, if we go back to the ICO Bulletin 121, published in 2001, statement there, but the key is see what lessons can be learned. Even though this document was titled Lessons Learned, it's see what lessons can be learned, and you need to read these things to understand the lessons. And one of the things when you start reading consecutively failure reports, you come up with a disturbing and recurring theme. It's that quality, the failure resides in the design, the problem is the standard of the engineering, inherent vulnerabilities in the spillway designs, deficiencies in the engineering practice. Those are things we engineers can address. We can't address some societal issues, but we can improve the quality of our engineering. Failures are continuing to occur. I think it's because we have better reporting that we're seeing a higher failure rate. It's not that more dams are failing, it's just that we now know that the number of dams that are failing. So we can no longer hide. You know, the failures are out there, everybody's talking about them, we need to do something about them. And this saying, you know, I was reading a book on evolutionary biology. It's the success of species. So success requires avoiding many separate causes of failure. We're engineers, we have to identify each and every possible cause of failure for our tailings dams and provide a design control, multiple design controls for each of those failures if we're going to succeed. If we miss one, we have a failure, but we have to catch them all. And failure mechanisms and causes are not the same thing. This is ICO Bulletin 121. It's the statistics what people like to play with of the causes, the mechanisms of failure. And so I'm a geotechnical engineer. I have to provide a defensive mechanism for each and every one of those failure mechanisms. However, when you read some of these reports, the incident was caused by a complex interaction of relatively common physical, human, organizational, industry factors, starting with the design. So we, the engineers, we have to understand what all those complex factors are so that our design accommodates those. So we don't just have to accommodate the physics of the problem, we have to accommodate the cultural issues related to the specific problem that we're dealing with. Good friend of mine, J.T. Thomas, he was a driller, we'd be standing out in the mud, and he'd be saying, you know, good judgment comes from bad experience, so you should be happy you're having this experience because you'll get better judgment. If we reforecast that for tailings engineers, for engineers in general, good engineering judgment comes from understanding the lessons available from the existing bad experience. You don't want to have your own bad experience, you should learn from the existing bad experience. Therefore, where do we find it? The lessons to be learned are found in reports of forensic investigations and inquiries. And I've put a couple questions down there that you should be thinking about when you're reading these. What decisions would I, the engineer, make if faced with the same situation and information? This is where you really learn how to do decision making. And you have to avoid hindsight. So I know it failed, so I'm not going to make that decision. Not knowing it failed, what would you do? And another one for engineers of record. This is the important one. At what point would I, the engineer of record, stop operations at the facility so that investigations and design modifications could be carried out to rectify observed performance issues? That's the key one. If you're an engineer of record, you have to be prepared to do that. You have to be prepared to stand up and say, stop. You can no longer do this. We have to fix it. So let's go back to the case history. Recent failure, Aberfan, 1966. Coal tip failure with 144 fatalities. Freely available inquiry reports. You can go and get them off the internet. The key thing when you read this is you realize that Aberfan failure in 1966 was not an isolated event. In the region, looking back to 1939, this is another failure. You had tip over a spring, so dumping on a poor foundation, heavy rainfall, ominous movements just prior to the failure. Day of the failure, the toe moved. You had a mobile run-out flow slide, 1,430 feet. It talks about a terrific speed. So if you think this is in the area that they were working on, there's a history of doing these type of things. Failures occur and you get mobile flow slides. 1944, at the same site now, not just in an adjacent site, on this site, there was this flow slide failure. 1944, so different tip, same site. Got to be internalizing this and knowing this and working forward on your designs to say that I have to prevent these things. Now on the same tip, 1963, they had a failure. Mobile flow slide resulting from it, stopping just above the school. That was the result of the 144 fatalities. So we were accumulating this experience and nobody's listening. And then we have the event in 1966 that resulted in all the fatalities. So all that happened was it ran a little further than the previous 4 incidents that had occurred. So, you know, we need to learn from these type of things. Very good report to read. Comment from the inquiry, discussion there. So there's lots of words on this screen, but I don't expect you to read them all because you're going to go and get to your reports and you're going to read them anyhow. So, you know, glance up there. But this was caused by ignorance, ineptitude, and a failure in the communications. So a failure in communications. How am I, the engineer, talking to multiple audiences, explaining to them why the things we were doing is important? So some of the recommendations, I'm going to repeat these later. You know, you should consider the structures we're building, engineers' structures. You should use civil engineering principles. You should have a civil engineer's experience in soil mechanics. He should talk to the geologist. You should use qualified engineers. They should be competent. You should have an inspection periodically by an independent and qualified engineer. And he should do that on an annual basis. This is 1967 that we're getting this set of recommendations. And if you read, as we'll see, later ones, they're the same. So what have we learned as an industry? The standards which should be called in for large tips adjacent to inhabited properties should be set, and we have to decide if we want lower standards for sites with lower consequences. And the definition of a large or potentially dangerous tip for statutory purposes, that sounds like CDA, dam classification, dam consequence classifications. Aberfan sent a message to the geotechnical and mining industries about the importance of collecting data on and learning from previous events. The message remains current. That's the 1967 statement. The message remains current. 2019, it's the same message. They highlight, in particular, they highlighted the need for proper understanding of the hydrology and hydrogeology of tip sites and of the materials upon which the tip is constructed, as well as proper management of the tips themselves. So this is 50 years ago, over 50 years ago, we're being told certain things, and we need to learn these. So let's just jump ahead. There's a whole set of failures that have occurred between 1966 and 2014. I tried to compile a lot of those, but it doesn't fit into a talk of this length of time. So tailings dam failure, no fatalities. Wake-up call for the industry, though. Here's a report. So you can go and get it. And the key is there's a lot of appendices. And when you read the reports, you need to read the appendices because a lot of the things that you will learn are in your interpretation of the information provided in the appendices. So independent expert engineering report, panel report. Then we had the Chief Inspector of Mines put out his report, and an appendix to that was the Kohn-Krippenberger report on the assessment of failure mechanism. So you've got multiple reports that you can read and understand the Mount Poly situation. Consequence of that was they changed the mining code in BC. They created a guidance document for the changes to the mining code of BC, and then the engineering BC organization put out the site characterization for dam foundations in BC. It's a guideline that I must follow as I'm an engineer working in British Columbia. And it basically says, engineer, talk to the geologist, talk to the hydrogeologist, talk to the hydrologist, get an assurance statement from them that you've properly interpreted what they're telling you. Chief Inspector Mine conclusion, pretty straightforward. The failure, the mechanism was sliding on a weak clay layer in the foundation, so it's a geotechnical issue. The dam breach was hydrologic, it was overtopping. And the root cause was organizational. So if we look at ICOLD and see where we're going to drop, the failure mechanism was foundation. Overtopping, that was the breach mechanism. But if you read that last box, related to the Aberfan inquiry, you go, failure on the part of those having knowledge of the factors which affect tip safety to communicate that knowledge and see that it was applied. So there's a direct correlation from 1996 to 2014. Some of the other conclusions of the report panel. Panel concluded that dominant contribution to the failure resides in the design. And there's other pieces there, but basically that's the key. We have to work on the design if we're going to improve the performance of our structures. I'm an engineer, I can affect design. I'm an engineer, I can't affect society. So I'm focusing on the design part. I'm talking to the engineers. A very important part, we see a lot of reference to the observational method. We are going to invoke the observational method so that our dams are safe. But from the Mount Poly report, it was the lack of recognition of a critical potential failure mode resulted in a misapplication of the observational method. And down at the bottom, the last line, the remaining problem is that the observational method is useless without a way to respond to the observations. So you have to go back, get Ralph Peck's paper from 1969 and read it. There's 8 short things you need to do to properly incorporate the observational method. And one of those is to decide that it's appropriate because there's many exclusions to using it properly. From that same report, review boards. So review boards are what's going to prevent the tailings dams from falling down. Well, it's part of best practice. That's all we're saying is that it's a part of best practice. But if you read the end of it, but they should not be necessary for all tailings undertakings. So the industry has to decide where can they best apply the very short pool of independent reviewers to reduce the consequences of the tailings industry. All facilities don't need the panels that you've been talking about and listening to on their projects. There's just not enough. You know, if we needed $3 billion worth of engineer records, if you have 3 people on a panel and you do the multiplication, it's a bigger number. Within BC, in the mining code, it says that Independent Tailings Review Board provides non-binding advice and recommendations, but does not direct the work or perform the role of the engineer record. The review board can't take over the design. The authority for design has to be vested with the engineer, and the responsibility for operation has to remain with the owner. So it's very important to understand that when you're looking at what you expect to come out from a review board. They had what at the time were thought controversial recommendations for best available technology. And so, you know, really if you look at it, it's design philosophy to provide redundant controls on the failure mechanisms is what they were saying. Number 1, eliminate surface water from the impoundment or reduce it as much as practical. Reduce the consequence of the failure. Promote unsaturated conditions in tailings and drainage provisions and achieve dilatant conditions throughout the tailings deposit by compaction. Very simple. You know, you look at what they're really telling you to do and you can incorporate it on many facilities. However, it's not new. Providing unsaturated conditions. Tailings Bulletin 97, ICOL, published in 1994, goes straight to the core of how do we successfully implement drainage. And if you look at one, it says, so we need no longer be, upstream dams no longer need to be regarded as a type that traditionally has a low factor of safety if you implement drainage. So you can go and grab this document and you can read about what people were thinking about in 1994 to improve the stability of upstream constructed tailings dams. ICOL Bulletin 21, promote unsaturated conditions. The filter under drainage system is a critical facility that has been overlooked in the past. So, you know, we're getting multiple times that we could have learned this lesson. It's about time we did. Aberfan to Mount Poly, you know, what changed? So here are the recommendations following Aberfan. Just threw them up there again, those 5. First one, direction under the engineer record. So that's coming out of Mount Poly. Operation under direction of tailings qualified person. So you have to have people who understand the structures, you're using them. Direction of a civil engineer, that's the engineer record. He has to talk to geologists, that's BC's foundation characterization guideline. Qualified engineers, chief inspector of mines recommended competency, professional reliance standards. Dam safety reviews by the engineer record on an annual basis, same thing. Just different words. We go on to the next recommendations. You have to have standards. Well, here we have Canadian Dam Association Dam Safety Guidelines. And then we have the consequence classification. So you can see that we haven't really moved forward from 1966 to 2014. We've implemented some of the things, but you know, we're still having dam failures. We get to 2015, Markel. Questions to contemplate when you're working through the report and all the appendices. What decisions would I, the engineer, make if faced with the same evolving situation and information? It's not like this dam was performing perfectly and then it failed. And at what point would I recommend stopping use of this facility to investigate decisions and develop a plan for remediation and return to operation? There's a report. The best part of the information is in the appendices. You have to read those appendices. It takes more than a weekend, but it's well worth doing it. Additional reading. So you need to go and get Steve Vick's paper, GeoRisk 2017, From Deviance to Diligence. It's really a good paper to read. You know, it talks about engineering structures, it talks about NASA, it talks about some of the organizational issues that lead to failures of tailings facilities. Good paper, so that's a paired reading assignment. So this is my interpretation. It's a design concept. It was based on the successful operation of the Hermano Dam. Starter dam with a basal drain, slimes contained behind an upstream raised dam constructed of sand tailings to be fully drained, finds elevation below the sand so that you get no slimes within your sand, runoff from the upstream catchment, diverted around the structure and under through the culverts. So they're using some of the best practices that or technologies that were stated from Mount Poly. Draft Global Tailing Standard, requirement 7.15. The change management systems also include the requirement for a periodic deviance accountability report. I think this is a really big step forward. We put these in our as-built reports, but this is taking it out and has a separate document that says from when I started design in 1998 to today in 2019, this is how the design's changed, and this is how I've accommodated all the different issues. So I think this will be a really good step forward. So how did the section that failed compare to the design section, and how did this occur? So very quickly, performance startup, they had some construction issues and the filters didn't work, and so they had to change things. So they lifted the drainage system up to the top of the starter dam, and they continued to work. Then they got some sinkholes from the concrete decant structure due to construction flaws. So they adjusted the geometry of the dam that pushed the crest back, sits now in the slimes area. They had a beach criteria which they didn't respect all the time, so at times slimes were encroaching into areas it shouldn't. 2013, you're getting cracking, high phreatic surface, high on the dam. So they improved drainage. They put in a local filter in a buttress to fix that. 2014, it migrated up the dam, so we fixed 2013, it's higher, put another buttress on, and then we had the failure. So you see an evolving sequence of events, and you have to ask yourself, where would I intercede? That's the real learning from this one, is where do I intercede as the engineer of record? So you go from the as constructed to the design concept. You have a fully drained, unsaturated situation to a structure that has a high phreatic surface and slimes within the structure itself that resulted in the extrusion mechanism. This is not in our industry. This is something that happened that doesn't relate to us directly. However, it's really instructional to read this report. Orville Dam spillway incident in 2017. No fatalities, 188,000 people were evacuated on February 12, 2017. There's a report, marvelous report to read. It goes really into the organizational issues that we need to understand. Team comments. So this is coming out of the forensic report. Spillway was vulnerable by design. Why are we doing things like that? Making things vulnerable. They should be robust by design, resilient by design, not vulnerable by design. So why was that? Lack of internal design direction and review. Inexperienced principal spillway designer. So this is you young grads, people out with 1 and 2 years being assigned to do designs of significant structures without oversight. So if somebody was hired, well-educated, but lack of experience. Little consideration of precedent. They didn't go back and look at the causes of spillway failures at the time. History of prior failures were not considered. So they looked internally and they said, we've never had a spillway fail in our dams, therefore spillway failures will not happen, as opposed to saying, the industry's had hundreds of spillway incidents. Let's go and learn from those so that we don't make the mistake that somebody else did. There was a lack of communication between the spillway designer and the geologist during the design. Recurrent theme. I'm a geotechnical engineer. I'm going to do the geotechnics. I don't need to talk to anybody else because I know what I'm doing. I was taught soil mechanics, and that's soil, so what more do I need to know? Vulnerabilities in the design were substantially exacerbated during construction. So that's direct out, substantially exacerbated during construction. Why? Lack of the designer input during construction. And this is really a common problem that we have is I've designed something, they've taken it and they're building it in the field, they don't talk to me, they don't understand the assumptions that I've made in the design, what I've assumed the conditions will be. They open up the foundation, it's different. They may not change the design to accommodate it, or they may change it inappropriately. Specifications change during construction. How many times have you been in the field and you put pressure on because of time, budget? We need to optimize the construction, which is the code word for reduce the costs, so that we can get our bonuses. So we need you, the engineer, to relax the specification. Insufficient technical expertise in dam engineering and safety. So this is an industry-wide problem. Those who are responsible for oversight must have accurate and timely information about all the issues that could affect dam safety. How do you get information on all the issues that could affect dam safety? You can read these reports because they will tell you about all the issues on that particular failure. Shortcomings, this is really important, and Franco Aboni has pointed out to me many times the failings of engineers doing risk assessments. You know, we think about them as we're making a matrix and something will pop out in the corner and we're done. So shortcomings of the current potential failure mode analysis, PFMA, processes in dealing with complex systems must be recognized and addressed. A critical review of these processes in dam safety is warranted, comparing the strengths and weaknesses of risk assessment processes used in other industries worldwide and by other agencies. So a risk assessment is just not doing an FMEA. That's only a component of it, and we need to go to the risk assessment professionals to get assistance. Same as you need to go to a geologist to get assistance on geology, and you need to go to a hydrogeologist to get assistance on hydrogeology. Insufficient technical expertise in dam engineering and safety. Engineers assigned to address the safety of dams and appurtenances must not only be familiar with these dam safety organizations, must keep up with the current state of practice in dam engineering. You must go out and read, and part of that reading must be the forensic investigations of the failures. Insufficient priority on dam safety. There was no one in position of authority specifically tasked with ensuring that the balance is right. So why does the mining industry have an accountable executive? It's the one individual who's responsible for that. And how did that come out? Well, it's when we see they don't have that, we have incidents and failures. So, you know, our regulations, guidelines, and standards are a response to the behaviors of the structures that we're designing. The fact that this incident happened to the owner of the tallest dam in the United States under regulation of a federal agency with repeated evaluation by reputable outside consultants in a state with a leading dam safety regulatory program is a wake-up call for everyone involved in dam safety. I think we need to reforecast that for the mining industry. And it would be, this is only the most recent wake-up call related to the failures of our tailings dams. Because when you read the histories, you see that at the end of every one of these forensic reports. It's a wake-up call. Well, let's wake up and listen, guys. 2018, so Cadia Valley Embankment slump. It was a mobile slump. It wasn't a failure, with no fatalities. Questions to think about when you're reading this one. Would a risk assessment identify this hazard? Would you discount the hazard because it's not credible, despite the record of things like Los Frailes? Would you discount it just because of the low likelihood or the low consequence? Here's the report, there's the appendices. It's important to read the appendices. I want to keep coming back to that. Reading the report gives you an incomplete understanding of what you could learn if you read the appendices. It's a mobile slump, two-phase movement. Phase one, foundation failure, foundation movements, then triggered liquefaction, which caused phase two, which was a more mobile movement. The tailings acted as a load exacerbating the strain weakening in the foundation, but undrained strength loss in the tailings was not in itself a cause of phase one. You can go to the static liquefaction course. You can learn how to predict static liquefaction, but you don't recognize the coupled mechanism. You will not be designing dams which will be resilient and robust and prevent static liquefaction. And so you need to go and read this two-phase mechanism and understand it, and start looking at your sites, looking at the foundation and say, I've got an upstream dam, I've got a high phreatic surface, will I get sufficient movement in the foundation that I could trigger liquefaction? Small movements in the foundation that will trigger liquefaction. Other findings there was a complex geologic setting, undetected unit with the foundation. Sometimes we miss things, sometimes geologists miss things. The tailings were generally saturated as a result of the design. Well, why was that? Why didn't we respect the 1994 drainage for tailings dams documented from ICOLD? The surveillance data was indicating that was movement occurring in the dam, but the movements in the area of failure were larger than in other areas. And that should have triggered somebody to go, it's performing differently, the foundation is probably differently, I wonder why. Let's go and take a look. So, my comment is, when do you trigger reinterpretation of geology? And they also commented that the movements were accelerating, but INSAR, in hindsight, identified the same zone of movement. And on another project recently, INSAR has told us that the zone of movement is much larger than we thought it was. So I see the use of INSAR not as a surveillance tool, but as a mechanism to tell me, did I miss something? Is something happening that I didn't expect in my performance-based design? In summary, the learnings from the back analysis of the failure indicate that the following factors need to be considered in the safety level of the remainder of the embankment. And so these are, you go back to Mount Poly and you can look at those 3 things that we wanted to do. Limited drainage within the body of the TSF and a high phreatic surface. Storage of a large body of saturated liquefiable tailings behind the starter embankment. So, that design could have been changed, and we would have had the foundation movements and the foundation failure, but no release of tailings. So the slump, the mobile slump, was triggered by a small foundation event. Mount Poly breach was triggered by a foundation. So the overtopping occurred because of the foundation failure. So a couple of mechanisms. You go back and look at Mount Poly, just flagging it there for you. Promote unsaturated conditions in the tailings with drainage provisions. Now we get to the current one. Can't say much about that because the report's not been issued. However, for me, the almost universal surprise at the rapidity of the failure, that when I talk to people, surprises me. Why do we think that a liquefaction failure would be slow and develop slowly? We've read the case histories. Here's the case history. Jeffrey Blight's book, Geotechnical Engineering, the Mine Waste Storage Facility. Unrecognized text is something I recommend all you buy and read because he's got a section in there, Failures of Mine Waste Storage Facilities. Submergo, sometime in the 1990s. I haven't been able to dig this one out yet. Gold tailing storage, 30 meters high, really steep outer slope, 40 degrees. Abandoned for 20 years. Phreatic surface measured at original ground surface. So the phreatic surface has dropped 30 meters over the period that it's been abandoned. So it's an unsaturated mass sitting on the ground. It's reactivated for mine planning reasons. They started operating, the phreatic surface jumps up 20 meters in 1 month. They decide, that's not good, we'll stabilize it, we'll put a bund around the dam. So they built a bund, they discharged wet tailings into the interface between the structure and the dam. And then here's the quote. The Submergo failure occurred at 10 a.m. on a Saturday when depositing was not in progress. So nothing happening, worker out there. A maintenance workman was standing on a section of the wall that failed. He was standing there totally unconcerned apparently. According to him, there was a tremor and loud rumbling. He clung to the tailings delivery pipe and was let down gently as this subsided into the gap. Fortunately, no one was injured. So a small indicator for us as the industry that liquefaction occurs without notice and very, very rapidly. And, it's in the history. We can find these things and we need to design against it. A couple comments on performance-based design. This is where we're going, risk-informed performance-based design. We've now got a body of work in the public forum that we can use as engineers to benchmark our work for site investigations, for site characterization, for material characterization, and numerical modeling. Each of these forensic reports since Mount Poly has a very detailed discussion on each of those aspects. So we can sit down and say, okay, what are the best engineers in the world telling us to do and how to do it and how to think about these things. One of the other things I got out of that is it takes 6 months to a year to put one of these reports together. You can do an incredible amount of investigation, design, modeling in a very short period of time if you're focused. So when people says, this is going to take forever, the record says you can do it in a year. And how do I know? I read the record. So key to that is, it allows us to be able to develop the models that tell us how our dams are going to perform. We look at how the dams are going to perform, and then we develop our surveillance network to accommodate the performance. CADIA, the occurrence of excess pore pressure is a consequence, not a cause of the instability. So if you're surveilling your dam with piezometers, you miss this mechanism. Mount Poly, as a result, the few piezometers and clinometers were too far beyond the toe to produce critical data. Even more fundamentally, the piezometers installed were only capable of measuring static. They weren't able to give you an indicator that failure was imminent. It's only after the failure that you generate the pore pressures. So we have to look at what instruments we're putting in our dams, and are they surveilling the mechanism that we're worried about? And thank you. If there are any questions, I'm happy to take them. Dirk was worried.
Questions?
He asked me to talk to a conference of 450 people for 45 minutes. Then he told me there are 800 people here, so I said I get 80 minutes, right?
And then Terry spoke twice as fast. And so we really appreciate this, Terry. This is great. Questions for Terry? It seems to me sort of your underlying theme is that we need to be proactive instead of reactive.
Absolutely.
And part of what you're pleading for is that part of our proactive stance has to do with truly understanding what happened.
Yes, and it's not the mechanism, it's the cause. We have to focus on the cause. The cause is complex. It's a lot of interactions. So I'm designing dams and I have a performance objective. I can achieve that, but if the operator doesn't understand why I've asked him to do something and he doesn't do it, that's a problem. If other changes occur, if the geology is not as interpreted, we have problems. So, it's multifaceted, and we have to realize that. It's not the finite element analysis which is the answer. That's only part of the design process. Understanding who I have to deal with is crucial. My designs in different jurisdictions are very, very different. If I don't trust, I provide redundancy and robustness. If I trust, then I'm optimized. So we have to be thinking that way. It's very, very important.
Hello.
Thank you.
Hello. I'm a tailings engineer, as differentiated from a geotechnical engineer. So most of my work is around designing and modifying how tailings deposits function. I think I really like your message about going back and finding the reports and going through those components. As somebody that's not heavily involved regularly with design and assessment of dikes, I can go online and I can do web searches for reports, but is there a more centralized or vetted or curated list of key reports that somebody would be able to go and get a list of it, at the very least read these 10?
It doesn't exist. It doesn't. No. And it would be useful to have that. Exactly. So I'm just pointing out that these are vetted reports. And so start with some of these.
No, I've got the microphone over here. Terry, Alan McConnell from Australia. You can tell I'm from there because I don't have an accent. Terry, listening to what you've talked about and other things at this conference, it occurs to me that the engineer of record has an absolutely terrifying role at the personal level. Is this true, and does this impact on people volunteering to be engineer of record?
For me, I don't see a difference from what I was doing 20 years ago. I was still responsible. I understood I was responsible. And so all that's happened for me with the engineer record is in BC, I have regulatory authority to do things. And so my job just became so much easier because I can slap people who aren't doing what I want them to do and say, I'm going to the government. I have to go to the government by regulation. And so, and performance is improving. That cycle of argument has been stopped. So for myself, I'm really enthusiastic about having the engineer record and trained in regulation because it gives the engineer record authority to direct actions. A problem I see is Engineers don't understand that we direct things. We write specifications, which are directions. So we do all our design work, we create drawings, which are directions, and specifications, which are directions. And then we start operation and we get uncomfortable with directing things. And now we make recommendations, and we make strongly recommend, or we recommend again. But we should just be stating in our documentation of the engineer record, you are directed to do this, and then there's no uncertainty on priority.
Last question, please. Thanks, Brian.
Brian Watts here. Terry, that was an excellent presentation, and everyone should heed those messages. They were very good. Having been through a number of forensic investigations, I'd like to just come out with a couple of common themes. And having read all the reports that led up to, by the design engineers that led up to the final failure, I can say without equivocation that most of the engineers, 90% of them, thought their design was conservative. And this word conservative was repeated over and over and over again. So when I read reports now, a litmus test for me is that word conservative in there? Does the engineer actually believe he knows the answer? That he's some sort of godlike figure and actually thinks he's conservative? So be very careful. You're not conservative unless, as Terry says, you understand the case history record. You have no way of understanding whether you're conservative or not. And conservative doesn't mean that you're using, upper bound parameters in analysis. You have to understand the case history record. That's the first point, and you've made that point very well. And the second is, coming out of Mount Poly, the sobering thing for me is that I knew some of those engineers on Mount Poly who were involved right in it. And some of those engineers and engineers on other projects I've worked on where there's been a failure, some of the best engineers out there. And you hear, well, how could they have made that mistake? How could they have done that? And somehow these people who make that comment almost feel they can't make that mistake. But one of the sobering lessons of Mount Poly is, if those guys can make that mistake, I said, I can make that mistake, and I better up my level of scrutiny here. And everybody should not discount the capabilities of those engineers, because they were very good.
I agree, absolutely. So a comment on conservatism. I've been reviewing a lot of dam breach and inundation studies, and people use the word conservative, and I always ask, what do you mean by conservative? In what context? You're giving me a result that is as far as we could possibly conceive so that we protect everybody if the dam does break? Or is it, I've been conservative on, I'm pulling it back a little bit because everybody's uncomfortable? We got to chase the word on conservative. I absolutely agree.
Terry, thank you very much.
Thanks, Dirk.
Be a speaker here this morning. We really appreciate it.